I want to look at a few more examples of circular motion, horizontal circular motion. We're going to look at the scenario of where friction is involved. So imagine a car sort of turning around a corner. If you think of yourself in a car next time you're with someone else driving, you yourself will lean off to the opposite direction of the turn. Your body's wanting to go in a straight line. Your car is turning in a certain direction, and what allows that car to turn is the grip of the tires. Okay, so just very quickly, I'll just show you a few examples of cars turning around a corner. We have there's a driver here demonstrating drifting, which is where there's an element of your tires slightly not gripping. The back tires are sort of sliding. The front tires are actually effectively doing a proper track along the road. So you can see the back end of the car hasn't quite gripped properly, but it helps it turn the corner more quickly. But the key idea is what's effectively keeping that car not sliding off into the undergrowth is an element of friction. Okay, the front tires are gripping very well. The back tires are sliding out slightly, but there's a sweet spot that driver is able to get where that sort of ultimate. He's not understeering, he's not oversteering, he's just keeping to the turn, and he's not sliding off into the undergrowth, or nor is he sort of oversteering and ending up tail spinning around. Okay, so what we're going to look at is the forces that are occurring as a result of that friction, and I'll show you another example actually, where this is not drifting. This is more of a sort of grip driving. The car being driven a little bit more sedately by James May is just that all the four tyres have got a reasonable grip, and he's able to turn the car, and the grip ensures that the car does actually turn as opposed to drive in a straight line. So the friction that is caused between the tyres and the ground is what allows it to turn. Now, just very quickly again, we have another scenario where you might have a sort of turntable, an object on a turntable. It's the same principle. Okay, so just to show you the example here, again we have an object. It has a radius away from its center, and it has a linear velocity. And as it's turning, we can appreciate the force that. So imagine this is an object on a turntable. That object is not spinning off the table. It's a turntable. It's staying on, and it's going around in a circle because of certain friction that is occurring between the object and the turntable that it's sitting on. And the centripetal force, which is shown here on this diagram as Fs, that centripetal force is causing. Let me just stop it there for a second. He's speeding it up. The centripetal force is making sure that it stays actually sort of on the turntable, because it's pulling it in, it's creating that acceleration. That means it's not going off at a tangent, it's staying in a circle. We know that the net forces in the direction of the center, okay, is that centripetal force. And we'll look at various different scenarios where we've got other things going on, as well as friction. We might have a string as well, or a combination of a few different things. We're also going to look at the weight of the object and how that affects that friction. And we'll talk about that in a moment. If I carry on playing this, you're going to see what's happening is we're speeding it up. We're getting to a point where, and this is crucial in your understanding, generally speaking, with these questions, you're looking at that critical moment where the friction is just enough to keep it on its track, and any more, it's going to slide off. Okay, so that's sort of limiting moment of the friction just being at its maximum. So that force, the maximum force that can occur because of the friction that can occur, and we'll look at how we can work that out. As soon as that friction gets too much, as soon as it speeds up too much, the penny slides. So let's look at a question where we've got that scenario. So a car with a mass of 1,500 kilos is traveling on a level road around a corner. We have a radius 100 meters, and the coefficient of friction between tires and the road is 0.8. And just to remind you of the formula for friction, friction is worked out as the multiplication of that coefficient by the normal reaction. So if you have an object and something's happening, it's being pulled or dragged or pushed or what have you, whatever direction of travel is going in, the friction acts in the opposite direction. So something might be pulled along with the tension of a string, and the friction acts in the opposite direction. Okay, and that friction is calculated by mu multiplied by the reaction. So what's the reaction? The reaction is that normal reaction to the surface. There's the surface. And the normal reaction is the normal reaction that goes against usually the weight of the object. So that's a fairly standard diagram. You've got your mass multiplied by gravity giving your weight down. You've got your normal reaction opposite direction, and those two will, generally speaking, equal to each other. Net zero as such. You have your tension pulling forward, you have friction acting against the direction of travel. So in this scenario, it's a very similar scenario. If we imagine we have our car and it has a mass of 1,500, so its weight is 1,500 g. There will be a normal reaction in the opposite direction. We have a radius of our turn, so imagine it's turning. Our R from the center is going to be 100 meters. And there is a friction that is going against sort of where it wants to go as such, or the friction is the thing that's going to effectively pull it in. So the friction is acting in this instance towards it, is the friction is creating the centripetal force. Okay. And that is equal to mu r. So the absolute basic scenario of the car turning, the friction is the thing that's going against where it wants to go. It wants to go straight on, and the friction is going against that. It's pulling it in. So it's against it. The friction is acting effectively going against the direction that it wants to go in. It's stopping it from sliding off. Okay, so rather than sliding off to the left, it's going to keep on that turn as it goes around. So you can just visualize one of those two cars from the Top Gear videos you just saw there. Imagine looking from behind the car. That's what's going on with that scenario as it turns to its right. So resolving forces vertically, we appreciate that the forces up is equal to the forces down. So the normal reaction is going to be 1,500 g. Therefore, we can use that idea to be able to deal with the friction, which is mu multiplied by r. If mu is 0.8, given to us in the question, and we're multiplying that by 1,500 g, we can work that out as being 1,200 g in newtons. And so that is the maximum friction. If you have less friction, as in you're going at a slower speed, so you're not meeting that absolute moment where between sliding and actually turning, you can be going at a slower speed and needing less friction to keep you turning. But the maximum that this car, a 1,500 kilo car, can manage to have with the tires on the road is 1,200 g. So that is going to be your centripetal force. Anything other than that or greater than that, any scenario where you need more force than that, the friction's not going to provide it. So just going again to absolute basics, if we look at the horizontal scenario, we understand that F equals ma. So the force that maximum force we can possibly have is 1200 G. The mass is 1500, and that gives us, multiply that by acceleration, that's equal to the force. So F equals ma. So if we resolve that, if we rearrange that, we end up with 1200 G divided by 1500, and we get an answer of 4/5 of gravity, being the acceleration that's occurring when it's making that turn. Remember, it's not speeding up or slowing down. The linear velocity is constant, but its acceleration is occurring because it is changing direction. Now, in fairness, now it won't be often that you'll be asked that as a question, asked to work out an acceleration. You're more likely to be asked other things. So if we remember from our sheet we had from beforehand, we appreciate that acceleration is v squared over r, or we can appreciate as being r multiplied by omega squared. And we also appreciate that the centripetal force is mv squared over r, or we can see it as being mr omega squared. So we can use those formulas to be able to get us, depending on what we actually are given as values, we can use one of those to be able to work out an unknown. So here we're being asked to work out the maximum linear speed. So that's v. So I've got two options here. I can appreciate that if I'm wanting to know the linear speed, well, v squared over r is equal to a. So I end up with v being the square root of a multiplied by r. So we can do the square root of 4/5 of g multiplied by my radius, which is 100. And when we work that out, it works out as being 28 meters per second. Alternatively, if we hadn't worked out the acceleration, if we had just had our centripetal force, we can use F equals mv squared over r. Fill in what we know, 1200 G, the mass is 1500. The velocity we don't know, the radius is 100, and we're able to get v squared is equal to 1200 divided by 15, and therefore the velocity is the square root of that. And we get the same answer, 28 meters per second. So just be aware that obviously we've done quite a lot of questions where we've been using mr omega squared, but if you're asking about the linear velocity, you're needing to use the one of the ones involving v. Moving on to a new question. Here we have a scenario of a roundabout of some sort, turntable, and an object on that turntable. There will be some friction. It's not a smooth surface. So if we imagine some object, the object has a mass. Now, if we don't know what the mass is, we just say the weight is mg. We have our normal reaction in the opposite direction. And again, if we imagine this object is spinning around, there's a center of rotation. It tells us that center is 75 centimeters. So just remember to make sure that you turn it into meters. Okay. And the friction is dragging it, or you want the friction to be there in order for it to turn and not slide off. So that friction again is mu r. So we can resolve vertically, and we appreciate that the normal reaction is equal to the mass times by the gravity. There's no other forces acting. Then horizontally we can bring that expression in instead of r. So friction is mu times r. We're told that the coefficient of friction is 0.6. We have got a normal reaction of mg, and that is the friction, that's the force that's effectively giving the centripetal force. So if we appreciate, now we're being asked for the angular velocity here, so I'm going to use the fact that F equals mr omega squared. So 0.6 mg is my force, which is centripetal force. M we don't know, but you can see what's going to happen here. The radius is 0.75, and we're wanting to work out omega squared. So we're working out omega. And once the masses have been cancelled out and we've rearranged, we're able to get omega being the square root of 0.6g divided by 0.75. And that works out at 2.8 radians per second. So those two questions deal with either things turning and needing friction from a grip, like a car, or if you've got some sort of turntable, what have you, and an object from not sort of slipping off. This one is slightly different. So we've got a slightly more complicated scenario because we've got two objects, that's the first thing, and they are connected by a string. I can't imagine what scenario you'd actually have this, but we can actually look at the forces occurring and still work out what's going on. So two identical particles, we don't have their mass, we'll just call their mass m, and they're on a turntable, and they are connected by a string of length half a meter, 50 centimeters, half a meter. They're both at rest, so they're not moving, not sliding around on the rough turntable. We don't know what the coefficient of friction is. That's actually what we're wanting to work out. We know that this turntable has a angular velocity of 2 radians per second, and the center of that circular motion is from the outside one, it's 2 meters away, and from the inside object is 1.5 meters away. So how can we make sense of what's going on here? Well, to some extent it's worth your while appreciating the two objects separately, and we'll draw a little diagram showing all the forces of each one separately and get a sense of what's going on. So for the first object there, same as the previous questions, we've got our weight going down, we've got our normal reaction in the opposite direction, and they will equal to each other. And then we have the friction on the object that is pulling towards the center of the circular motion to stop it from sliding off. But we have an additional thing here. We also have the string, and that therefore has a tension. Again, the other object has the same scenario, it has a weight, has normal reaction, has friction heading towards the center, but in this situation there's a tension going, effectively pulling it in the other direction, or creating a force in the other direction. So firstly we have to appreciate the vertical forces. So we know that the normal reaction will equal to mg for each of them, for both of them, and we therefore know that the friction, which is mu times r, we don't know what mu is, but we can at least say that it is mu multiplied by mg. So that's for both of the both objects. So if we now look horizontally, we can appreciate, now we've been given omega, so I'm going to use mr omega squared. So the forces acting towards the center is both the friction and also the tension on the string, and that's equal to the mass multiplied by the radius, which is for this particular one is 2, and omega squared, actually omega, sorry, we know what omega is, sorry, we have omega as being 2. So we end up with F plus T is equal to 8m, And we can also appreciate that, well, we know what the F is. We can straight away say that it is mu mg. The only thing we don't know is the tension. Bear with us for a moment. If we look at the second one here, we've got a situation where in the direction of the centripetal force, we've got that friction. In the other direction, we have the tension. So it's subtraction, and we have, again, mr omega squared. Our r is going to be 1.5 for this second one. It's closer to the center, but the omega is still the same. So we end up with, now again, the force we know is mu mg, take away tension, and that's equal to 6m. So we have two equations, and effectively we can add those two together, and the tensions will cancel out. So mu mg plus t, and take and add on mu mg minus t, we end up with 2 mu mg. And if we add the right hand side, the 8m and the 6m, sorry, someone's at the door. Sorry about that, that was my Temu order. Anyway, so if we rearrange that, we end up with mu being 14m divided by the 2mg. The m's cancel, and we're left with 7 over g, which works out as 5/7. Now, they're fairly handy questions in many respects. You don't have any forces at an angle, so you're not dealing with theta and sine theta and cos theta and so forth, and resolving forces. But again, just organize yourself, get your diagram drawn showing all the forces acting, remembering forces up equals forces down, and you usually get something out of that. And then you apply that to whatever you can get out of that, to then look at horizontal forces, and the net force acting in the direction of the center of the circular motion is your centripetal force, and that is equal to mr omega squared, or mv squared over r. You should now be able to have a go at question from exercise 7c. You should be able to have a go at questions 1 to 5 and also question 11.